I talked about booting Linux and running interesting workloads, but now the question is, how do I actually build Linux and run interesting workloads? So that's where we have another tool that comes in that's called FireMarshal. So FireMarshal is our software workload management tool that kind of builds the software stack for you to run your tests. So in terms of the tutorial roadmap, so we covered a lot of things, but we haven't talked about software yet. We basically kind of just said the software magically gets built for you, and then you can run it in bare metal simulations or in Linux. So if you look at software workload management, there's tons and tons of things that you have to worry about. So not only do you have to worry about building the binary itself, if you're running something like Linux, you need to make sure that you copy the proper files into the file system so that you can run your binary with it. So you have to modify not only binaries, but file systems. What's actually outputted from the simulation? Is it just a UART log? Is it a file that's dumped in Linux? Like, are you writing out a text file that you need to dump out? If that's where you're putting like printfs, right? There's a lot of inputs and outputs into the simulation itself. What about it being repeatable, right? We talk about a cycle-accurate deterministic simulation with FireSim, but we need to make sure it's the same thing for software as well. And then what about the different levels of simulation? In Jerry's presentation earlier, we talked about target level simulation, right? I'm just simulating a config with some like simulated models. How do I move that simulation to FireSim? How do I run it in functional simulation, right? There's multiple different ways that you can simulate your particular design. And then, of course, we like kind of the sharing aspect here. So how do you actually share these workloads with the community, right? Do I just give a bunch of people a bunch of like bash scripts and then hope it works for them? So how do I actually do this dependably? So that's where FireMarshal comes in. It basically wraps all of the things that you might need for software in a particular API that allows you to interact with things in Chipyard as well as FireSim and other simulators. And it provides hooks for it as well. So what's the actual co-design flow for when you're trying to make a new accelerator or make a design and test it with your software, right? So you have a lot of requirements. So you have some sort of spec of what your accelerator is going to do, right? I'm going to accelerate matrix multiplication. Call it what you will. You maybe have a functional model. Now that I have the spec, I can actually run the matrix multiplication, right? I have a bunch of hardware and software potentially. I have maybe some binaries, some RISC-V, like Linux binaries. Maybe I have some RTL for it. You know, they exist for it. And maybe I have a simulator, right? So I need to be able to change anything with respect to the software so that I can run either on the functional model or in something like FireSim. So in this case, we also have RTL. I don't know where the images has come from or generated, so we're going to talk a little bit about how that's actually generated, right? We have Linux, we have OpenSPI. I'm going to start naming a bunch of random software tools. I don't know if I even know all of them. But the point is that there's like a large corpus of software that exists for RISC-V that we need to somehow kind of bundle up and put into a binary or put into an image so that we can run our stuff. What about initialization scripts for the particular operating system, right? Or how do we actually build the software, right? There's a lot of different scripts for that as well. What about like sharing it around? It's confusing. So basically, we want to give a single source of truth, a single specification of the software itself, so that we can actually pass that to someone else or actually drive Linux builds, Linux compilation. So it's a little bit abstract right now, but we'll actually see it when we type some commands. Additionally, we have different types of simulation. We have functional simulation, which was fast. We did it with Spike earlier this morning. We ran some of the stuff in Spike. What about FireSim? FireSim is also fast, but you know, sometimes it's not as fast as actually running the real RTL on an actual taped out chip. So is the software exactly the same? Sometimes it can't be, right? So how do I encode that nicely in some of these workflows here? So we want to make sure that we can actually target each of these flows easily with this same exact kind of workload specification. So this is where FireMarshal comes in. And I'm going to talk a little bit about the FireMarshal workflow. It basically is first starting off with specification. So first, you're specifying a workload, which involves basically a hierarchy of specifications specifying what exactly you're building. So what does that actually mean? So what is inside of a workload. This includes things like sources. So if you're doing things like Linux, you're doing things in QEMU, adding extra extensions to QEMU, OpenSPI. It has all of your inputs and outputs. So what exactly do you expect to copy back from the simulation? What do you expect to copy in from the outside world? Any sort of initialization scripts, and then a variety of other things, right? So basically any sort of input or output that needs to say what your software workload is. So this is where this kind of hierarchy comes into play here. So basically, workloads are kind of the blob of things that you need to run a software, or it's a blob of things that you need to build whatever software that you need. So in this case, we basically provide some sane defaults for a set of blobs. In this case, this blob of thing that I'm building right now is build root Linux. So we provide a sane set of defaults in a particular file that's called brbase.json. And then for your benchmark, if you don't care about modifying any of those defaults, you can then extend it, add your own individual software configurations, aka I'm running a particular file, I'm catting out something in Linux, I don't know, I'm running Vim, creating a file, whatever the case is. You add your own modifications on top of the same defaults. And then, of course, I can continue kind of that trend. So if I have some common files here that I'm maybe copying into a simulation, I can then have another workload that says I'm depending on those common files. So you can see how this kind of inheritance comes down the line, where basically you can have reusable snippets of configuration for your different software. And again, well, I'll actually show you what this looks like. So when I talked about this build root thing up at the top, this is basically what we call a board in FireMarshal speak. And it's basically the same defaults for running something in FireSim, in this case, a build root configuration of Linux. We have equivalent ones for running things in bare metal. And then, of course, as I mentioned, you have arbitrary inheritance. So what you would do in this case, if you're trying to run something like spec, for example, is you would depend on brbase.json that says, I'm going to boot Linux. This is how I boot Linux. And then all you have to do is add your particular binary that you want to run, your spec binary, for example, and then you're good to go. So we specified something, and I'll show you examples of what that looks like in a second, but let's actually finish out the workflow here. The next step is actually building here. So when you build things, you actually type in a command, and then you actually generate either binaries or rootfs's, depending on if you're booting Linux or not. So when you actually build something, you basically have FireMarshal look at that specification of what's actually done, and then actually run a couple things. So it'll basically automatically build what you're running. So you provide it like a make command or build script, and it'll automatically run that for you. It'll automatically kind of parse that inheritance tree and build everything down the line to your particular benchmark, including building Linux. And then it'll finally generate your output image that you're going to run Linux with and your rootfs. Or in the case of bare metal, it'll output just the binary itself. So I guess the point here is basically you type a single command, and then it basically parses that specification. This is just some arbitrary output, and basically shows you, OK, here's where the output is in a particular log. Again, you'll see this in just a second. So for example, if I'm going through the steps here on the left, you're actually running the build setup a script. So for example, you're building a Linux binary. You're actually building out the rootfs, and then you're actually copying things around. So you're building out your final rootfs image if you're familiar with Linux, and then of course telling you where the output is, where all of your results. So we talked a little bit about specification. We talked a little bit about builds. Now is, OK, now I've actually built the software workload, and now I need to actually run it, albeit FireSim, Spike, whatever the simulator is. That's where the install command comes in. Basically, the install command is a way that you can add in your particular simulator. In this case, we're talking about FireSim and Chipyard, so we're going to be focused on FireSim workflows here, Spike and QEMU. But basically, you can automatically install it to these different tools and run them in that tool. So you have a single source of truth here, my benchmark.yaml file that I write. I build it, and then I can automatically use it across all the different platforms as long as there exists a hook. So for example, we're talking about these up here, running something in Spike or running something in FireSim. And I'll talk a little bit about what it means launch versus install. Again, these are all terms that basically turn in commands that you're going to type with Marshal. So I talked a little bit about launching here. So launching is basically the simulators that are built into FireMarshal. So in FireMarshal, by default, you have access to Spike and QEMU. It's the same Spike and QEMU that you might use inside of Chipyard. It's just calling them directly. And it basically automatically launches it for you, runs your particular workload, copies the results back. So it kind of manages your simulation here. So you can add your tool here if you wanted to and have Marshal basically launch it for you. So in this case, boot Linux, run the benchmark, and return the UART log. Now, what happens if you don't care about FireMarshal enough to basically add a hook to have it run the simulation for you? Well, that's kind of what FireSim does. It says, I want to have kind of a barrier between what FireMarshal is. I want to make FireMarshal just build me the binaries or just build me the rootfs's, and I want to manage simulation separately with my FireMarshal command or FireSim commands. So that's what installation is doing. It's basically a hook to export your workload, your software workload, to another tool. Again, so in this case, you have something like FireSim that uses it to basically export it to the FireSim land, FireSim's view of a workload, so it can run there. And of course, kind of with the theme of what we're talking about here, this is extensible to other simulation infrastructures, right? If you're not using Spike, if you're not using FireSim, but you want to run it in some different way, you can add a hook for your particular simulation or emulation infrastructure here and still use all the nice software building aspects of FireMarshal. And the key here is that this does not rebuild the workload. So this allows you to basically run the same workload on multiple different platforms. So, you know, there's a variety of reasons why this is nice, just like simplifying debugging, right? You have the same binary that's running on different things, and it ensures that there's some consistency between the two. So an example of invoking it would just be calling Marshal, this install command, and then a path to your particular workload. So I talked a lot about how FireMarshal works. Let's actually go into the nitty-gritty and do some hands-on stuff. So we learned a little bit about Gemmini from earlier. That's basically what you're running your target level simulations on. Now we're actually going to build some software for it. So in this case, we're going to be running ResNet 50 on a Gemmini SoC, first in software simulation in Spike, and then we're going to be running it in FireSim in the second here. And if you're not already aware of what ResNet 50 is, it's basically a deep learning model that's used for computer visions. I get an input image, in this case, Berkeley's wonderful tower, that I'm forgetting the name off the top of my head, so it's not that wonderful. And then the Berkeley tower comes out here, the label coming out of the other end. And then Gemmini is our machine learning accelerator. You can think of it as accelerating MapMol. So predicting images here. So let's actually look at what the workloads are. So I talked about two different workloads here, or a kind of default specifications. One is bare base, which is representing the bare metal workload, aka you're not booting Linux. It's kind of the simplest way of jumping into the main aspect of your program as fast as possible. And then BR base, which represents build root Linux, which is a stripped down version of Linux that runs pretty fast. So we have same defaults for both that are Marshal provided. In this case, we have Gemmini specific workloads that inherit from both. So this is going to be your ResNet and ResNet running on Linux, interactively or non-interactively, running in bare metal, and then in this case, MobileNet bare metal. And we'll focus on that in a future slide deck. So starting off with the interactive stuff. So go ahead and go to where these workloads are defined. So we're going to go to a CYDIR. So unlike the morning where we typed in M CYDIR, we're going to go to a CYDIR representing afternoon and go to software/tutorial. And then go ahead and look around in this area. There's going to be a Marshal configs directory. And this is some initial specifications that are pre-written for some of the software. You'll see a build script. You can look inside and see what happens. It's basically invoking make. So go ahead and do that. And then I'll wait a couple seconds for people to look around. Okay, so once you've done this, we're going to run a command that's going to take a little bit of time here. So we're going to go ahead and move to it. So once you've gone into the Marshal configs directory, so make sure you cd into Marshal configs directory, go ahead and run this Marshal build command. Again, doing what we specified earlier. This is actually building Linux. It's building the Gemmini deep learning binary for Linux and actually building Linux as well. So normally, if you're starting from scratch, this will take about 20 minutes the first time. But in this case, we ran it for you before, so it should be pretty quick. It should only take a couple minutes. And that's because the root FS that's being generated for build root is going to be already built for you. So you're only building a couple new things for Gemmini specifically. Once you're done with that, so that should take a couple minutes. Hopefully, you should start seeing output on the screen. I made sure to add the V flag so it looks nice and crazy on screen. Go ahead and run Marshal launch. So again, what we're doing now is, now that we've built the binary, we're now actually going to launch the binary in a pre-specified simulator, in this case, Spike. So that's what this command is doing. Launch the simulator inside of Spike, and we're giving it the same specification. So I guess as a show of hands, who has already typed in launch? Or are people still building? Okay. Okay. So we'll wait a couple seconds here. It is building build root, so it's building the rootfs as well as the Linux binary that's going to be used to boot. The launch itself is taking that binary and that rootfs and actually launching it in a simulator that's built into FireMarshal. So either Spike or QEMU, which are the two built-in simulators. Sorry, can you repeat that? Yes, Spike and QEMU. So QEMU is a RISC-V emulator. Yeah, fairly well known. Okay. Who has gotten to launching so far? Okay, great. So this is actually going to be booting Linux and then running ResNet 50. So I'll let this run in the background. You can see it kind of scroll along the screen. It should boot Linux pretty quickly, and then it has to run ResNet. And ResNet's kind of a big workload, so it's going to take a little bit of time, even in functional simulation in Spike. So let's actually dive into what did we actually do. So if you looked at the specification for ResNet 50 Linux, you should have seen something like this. And so it involves a couple different components. One, outside of just the base image, indicating that I want to run on Linux, brbase.json, and a particular name, it's specifying a build script that's going to be cross-compiling the Gemmini test for Linux, right? So I'm running a particular compiler that's made for RISC-V Linux. That's what this host init is doing. You specify also the command that I'm going to run when I boot into Linux. So when you boot into Linux, you're not going to get a prompt, a console that you can type the command. Basically, this will automatically inject that command for you when it boots, right? So you're not going to get a prompt. It's just going to run that command directly. So it's going to run root ResNet 50 Linux. The next thing that you might see is what happens if I modified Spike or whatever simulator that I'm running with if I need extra arguments. So you can add, basically, in this case, the functional model for Gemmini, so that when it runs a Gemmini-specific instruction, it uses the functional model for Gemmini. And you can also extend this to other simulators or different flags. For example, if you want to enter debug mode for Spike so that you can step along with your program and see what's happening step by step, you can add the Spike debug flag, right? So you can basically arbitrarily pass these flags to whatever your backend simulator is. Same thing for QEMU as well. So that's kind of the quick view of the specification. This is still going to be running. You should see Linux booting at this point. But let's actually talk a little bit about more complex use cases. So going into multi-node workloads here. So FireMarshal, we talked about it as kind of targeting one particular test for what you need to do, right? I'm running only a singular mapmol, for example, for my deep learning workload, or I'm only doing one prediction on a single machine. But FireMarshal actually extends this to target multiple different simulations at the same time, or multiple different builds of your software. So an example here is basically, for FireSim, what happens if I want to ping two servers that are connected to each other back and forth? So I can basically specify the job, very similar to before. I have kind of a name at the top. I specify that it's running Linux. I'm taking those sensible defaults. And I can basically have recursive implementations of FireMarshal specifications indicating this is a particular FireMarshal workload, and this is another FireMarshal workload that I'm going to reference. And each of these workloads are doing different commands. One is doing ping for 16.03, and the other is doing it to 16.02. So why does this seem useful? So this is useful because this actually plugs into a lot of other simulators, right? You can run multiple Spike simulations in parallel in this way. You specify it. You specify that the workload that you want to run multiple things in parallel. Then you can send it and launch it in functional simulation in parallel. You can send it to FireSim when you install it, and FireSim will run it in parallel as well. Another example here is basically, oh, yes. Yes, so by default, the workload doesn't specify that. That's up to the user. In this case, there's like no synchronization. They're just pinging each other. But in a multi-sim case where they're kind of talking back and forth, you can basically write your own binary or script that basically kind of adds some sort of synchronization or locks between them. Yeah, so again, we leave it kind of abstracted out, saying that we provide the support for making things parallel, but then it's up to you to kind of add the synchronization between the different simulations. Cool. So another feature is native initialization. So what does that actually mean? So you can imagine that you're compiling some sort of workload. Let's say you're doing some PyTorch conversion thing, and you want to convert the output of your accelerator, pass it to some sort of like PyTorch thing that's running, and then it's going to give you a number saying 5. The accuracy was 5% or something. That's kind of abysmal, but for the sake of this example, holds. So it's hard to actually compile something like PyTorch all from scratch. So what you can do instead is you can actually, before you even run your simulation, you can actually boot the operating system that you're targeting, build root or Fedora or whatever the case is, because we have multiple operating systems. You can boot the operating system in QEMU, a very fast functional simulator, builds your software natively in RISC-V on in that case. So in this case, you would basically boot beforehand in QEMU, type in yum install BLOS, Python, whatever, everything that's precompiled for you, type make, and then you basically save that result and use that in your actual software workload. So it basically allows you to install packages and natively compile things. So instead of having to use a cross compiler and figure out, okay, what's the rootfs that I'm targeting and all that gnarly stuff about software, you can just basically pretend like you're inside of the operating system, typing make, using the operating system provided GCC that's native to that operating system, and continue your work. So very useful. For example, I've used this to build entire databases for RISC-V without having to cross-compile it. I basically just typed in make for the database. Yes?
Is that part of the image that you would run using your actual Spike simulation, or do you create an extended image with as all of these things pre-installed, which you would as a base image to add your own benchmark?
So when you're doing the cross-compilation, it's basically going to be using, so in this case, these are the sensible defaults for Fedora. You would basically only be able to install, yum install, whatever, the defaults that are like pre-specified here. So if you need to install something else extra, what you would need to do is you would need to go and you would need to modify this defaults to basically, instead of it being like a minimal Fedora image, you would need to make it like a maximum Fedora image.
The question that
Okay.
Is that happening every single time I am starting my benchmark, or am I using this just once?
Oh, yes. Yes. Yes, this is only used when you type in Marshal build, so only once, when initially building the binary and rootfs. And then once you run the benchmark, at that point, it's already built. You can just go ahead and run it. Good question. Good question. Okay, so we talked a little bit about building binaries and making it a little bit easier, but what about actually getting whatever results you have and doing some sort of like graph of it, for example? So we talked a little bit about the FireSim results in the paper. When they ran on FPGA simulations, they presumably ran some sort of like Python script that was calling matplotlib to generate a graph for a paper, right? FireMarshal actually also automates this as well. So inside of the workload, you specify, I want the output to come to be like a CSV or whatever. Then this will get automatically passed to what is called a post-run hook. So you can provide it a script that basically says, whatever the outputs are of the simulation, here is the output folder that exists. Basically run the script on the output folder. So if you dump whatever your results are, the counters of an L2 cache to see how many hits or misses there were, you can take that and convert it into a graph or whatever the case is. Yes. This is running on your host. So this is after the target level simulation finished, albeit with Spike or whatever the case is. Then you return to the host, simulation is finished, then the script runs on the host. Yes, so in this case, you get a path to wherever your results were, then you can access the particular CSV here, and you can do whatever processing you want. So very useful for making graphs or whatever the case is after the fact. So now kind of returning to what you were running. So hopefully you should actually see results either still printing or done printing. Show of hands, is it done for anybody? Ooh, okay, so it takes a little bit longer, but that's fine. So I guess for this case, you should hopefully start seeing things like conv and then some number and cycles indicating that it's running. I don't know where it is exactly yet, but for right now, go ahead and click Control-C to exit out of the simulation so we can go ahead and move on a little bit here. And this is what you'll see at the end. Some nice log indicating I predicted 4 images with particular scores. This needs to be converted into a percentage. So you could run a post-run hook to actually convert that into percentage, but you're predicting 4 image classes. And then some other miscellaneous statistics. Okay, so after you've clicked Control-C, you should have ended the simulation. We're next going to set up for the next section, which is actually exporting things to FireSim. So in this case, we're actually going to install and build a workload that we're going to be using for FireSim, which is MobileNet. So MobileNet runs a little bit faster, but it's basically doing the same thing. It's predicting images, and it's giving them a particular name, saying it's a dog or a cat, or whatever the case is. So go ahead and run these 2 commands inside of the Marshal configs folder, which you should already be in. So Marshal build MobileNet, then Marshal install MobileNet. So I'll give people a couple seconds for that. Make sure I'm on time here. I'll be giving people a couple minutes early break. Okay. How many people have run those 2 commands? Perfect. Okay. So great. So since it's bare metal, it should be pretty quick. You're not compiling anything for Linux. You're just running it directly without an operating system. So it should be pretty fast. And you run install. If you remember, install means in this case that I'm actually going to export the software files to FireSim. So let's actually look at what FireSim it has installed. So go ahead and cd into fdir deploy workloads, and go ahead and cat that file or open it in Vim, whatever your editor is, so you can actually look at what was exported. And we'll go into detail about what this looks like, but this is basically the API between FireMarshal, the software building tool, and FireSim, what actually runs inside of the FireSim simulator to understand this is the binary that I'm going to run, this is the name, here are outputs, whatever the case is. So go ahead and look at that file. And I just want to say that there's a lot more features. I think that's kind of apparent with all of these tools. There's many, many more features that we don't have time to get into for this particular tutorial. We kind of do the blazing fast approach to make sure that you touch everything, so you actually look at a full workflow. But there's many other flags and features that are provided inside of FireMarshal that you may not have seen that are very, very useful. So we have, of course, a lot of documentation on FireMarshal about the API and how to use it, both inside of Chipyard and as well as in FireSim. So I urge you to look at the documentation.